Welcome to structural dynamics class. So in this class we will study modal orthogonality or orthogonality of mode shapes. So let me give you a background of this modal orthogonality. In multi-degree of freedom system, when we idealize the system into n single degree of freedom systems, so that means what, in modal analysis, n degree of freedom system we convert into n single degree of freedom systems. So the process in which we convert this n degree into n single degree of freedom system, we use a transformation matrix. So this transformation matrix is nothing but modal matrix. So mode shape or modal matrix has a property to convert or to change the coordinates from u to q. So as you know, we have used u is equal to phi and q term for denoting our response. So this phi has a ability to transform the from u coordinates to q coordinates. So how it is able to transform that? So that properties we are going to discuss today. So modal orthogonality we will discuss, and then one example problem also we will discuss to prove how mode shapes are orthogonal to each other. So this is a idealized mass spring and damper system or lumped mass system. So where forces are acting at level 1, level 2, level 3, that is P1, P2, P3, these are the forces. M1, M2, M3 are respective masses. K1, K2, K3 are stiffness terms, floor stiffnesses, and damping 1, C1, C2, C3 are damping terms. So for undamped free vibrations, we know equation of motion, that is in the form of mu double dot plus k u dot is equal to 0. So that means what, all these forces are zeros. So response is dependent on both time and location of the mass. So like that's because of which we describe displacement as u is equal to u of x and t. So in continuous systems, this x is a variable starting from 0, that is base, up to the total length of the structure. But in lumped mass system, that is multi-degree of freedom system, what we do is this x will have some discrete values. So in this case, x will have, say, if the floor height is 3 meters, so this is 3, this is 6 and this is 9, and time is continuous. So time is continuous from 0 seconds up to which we want response in free vibration, and in forced vibration till the time force is lasting. The equation involving u is called coupled equation. So for deep coupling that, we need to use the properties of phi, and u is equal to phi of x and q of t. Now what is modal orthogonality? So we already discussed that, like how this characteristic equation can be derived from equation of motion. So let me give you a brief details of that. Mu double dot plus ku is equal to 0. When we use u is equal to phi q and q is equal to some a cos omega t plus b sin omega t, and if we double differentiate that, what we get is m omega square phi q plus k phi q is equal to 0. So from this equation we can write k minus omega square m bracket phi and q is equal to 0. This we had already discussed. So q cannot be 0. For non-trivial solution we need k minus omega square m into phi should be equal to 0. So for q cannot be 0 for non-trivial solutions, and then so phi also cannot be 0. So m minus lambda k minus lambda m should be equal to 0. Phi cannot be 0 because phi and q cannot be 0, because if they are zeros then u will become 0. So for non-trivial solution both cannot be 0. So we will be left with k minus lambda m is equal to, so that is the equation here, multiply by phi is equal to 0. Phi cannot be 0, so that is what we will find out now. Then from this we can write k phi is equal to omega square phi m. If omega r is the natural frequency of rth mode and phi r is the mode shape of the rth mode, so omega r and phi r are natural frequency and natural mode shape of rth mode. If we substitute that in it, so it should be k times phi r should be equal to omega r square phi r into m. So it should hold good for any mode shape. So this is equation number 1. Then the same should be true for nth mode. So that means what? We can write k phi nth mode is equal to omega n square. This is nth mode, phi nth mode into m, both are equal. So it is equation 2. So now we will do some operations on this one. So let us pre-multiply equation 1 with phi n transpose and equation 2 with phi r transpose. So let us now look at what will happen to first equation, phi n transpose. So here I am multiplying this equation with phi n transpose k phi r here. Phi n transpose k phi r is equal to omega r square phi n transpose m phi r. This is equation number 1 when we multiply with phi n transpose. Then if I take transpose of this one, phi n transpose k phi r whole transpose is equal to phi r square phi n transpose m phi r whole square. Now in transpose, if I take this transpose, what will happen is in transpose these terms get reversed. So it will become, transpose value will become phi r transpose k phi n. So this got reversed, and omega r square exactly same, and this one again gets reversed, phi r transpose m phi n. So this is a matrix property. So if A, B, C, if we take whole transpose, what we will get is like C, B, A will get. So say C, B, A will get. Then similarly when we do equation number 2, in equation number 2 what we are doing is we are multiplying it with phi r transpose. So phi r transpose k phi n is equal to omega n square phi r transpose m phi n. So we are pre-multiplying it with phi r transpose. You can see, look at this one, phi r transpose. Now if we look at equation number 3 and equation number 4 and subtract 3 and 4. So that means what? 3 from 4 if I subtract, what will happen is this term, the first term here and this term here, both are same. So if I subtract this one, what I will get is, you can see phi r transpose m phi n, this is common in both. So what I will get is, so these left hand terms are same, so that means answer is 0 there. So omega n square minus omega r square into phi r transpose m phi n is equal to 0. So now what this tells us is, if n is equal to r, then this is 0, the entire term is 0. But if n is not equal to r, then this term should be equal to 0. So that means what? Phi r transpose m phi n should be equal to 0. So similarly we will get another relationship, something like this, phi r transpose k phi n should be equal to 0. So that means what? If we do pre-multiply and post-multiply any matrix with modal matrix, we will get all the diagonal terms only. So that is what is shown in this equation. So how do we represent that? So if we write say phi 1, phi 2 and phi 3 here and write these terms. So this is something like x, y and z if we write, and then represent modal matrix or so modal vector in the coordinate system. So then what we will get is, so any line what you draw for each mode shape in the coordinates, these 3 lines will be perpendicular to each other. So that means what? Mode shape 1, as it is something like this. So this is mode shape 1, mode shape 2 and mode shape 3. So mode shape 1 is perpendicular to 2 and 3, and mode shape 2 is perpendicular to 1 and 3, mode shape 3 is perpendicular to 1 and 2. So that is what is modal orthogonality. Now let us look at the problem and try to understand by using numerical values. So the structure, the same example we have solved in the earlier class, the same problem I am taking. So where eigenvalue is performed, so we know that in week 7 module 2 we performed already this analysis. So we get stiffness matrix and then we have mass matrix. So you can clearly see that mass matrix is already diagonal. So off diagonal terms are 0, but when it comes to stiffness matrix, some off diagonal terms are there. So that means what? If we write equation of motion, what we will get is, we will get coupled equation. Coupled equation means in the same equation we will have u1 terms, u2 terms, or u1, u2, u3 terms together, or u2, u3 terms together in 3 different equations. So if we have one equation, if one unknown is there, we can find out. So one unknown, its derivatives are okay. So that in differential equation, say if u1 is there, u1 dot, u1 double dot is all right. But in one differential equation, if we have u1, u2 and u3 or its derivatives, we cannot solve that. So let's go further. So these are eigenvalues. So if we solve this matrix k minus lambda m, determinant is equal to 0. When we solve this one, we get lambda 1, lambda 2, lambda 3. Upon substitution of each lambda 1, we get so lambda 1 means corresponding natural frequencies, So lambda 1, lambda 2, lambda 3 and omega 1, omega 2, omega 3 values are there. Corresponding natural periods are given. Now if we substitute lambda 1 in the equation, say this equation k minus lambda 1 m into phi is equal to 0. So when we solve this one, how to solve this one we have already discussed in the previous lecture. So when we solve this one, we get phi value which is corresponding to lambda 1, so that is phi 1 we get. So like that, first mode phi 1, first level, so second level, third level. So phi 1, phi 1, phi 1, phi 2, phi 2, phi 2 and phi 3, phi 3, phi 3. This is mode 1, this is mode 2 and this is mode 3. So values of this mode 1, mode 2, mode 3 are known. So this is first mode, this is second mode and this is third mode. So what we are trying to discuss in this class is how these things are orthogonal to each other. Like matrix wise, if we solve phi transpose k phi. So this is phi transpose, that is modal matrix. This is k and this is phi transpose k phi. If you solve this one, we are getting this diagonal term. So how do we multiply? First this and this we multiply and the product of that together we will multiply with this one. So we will get this matrix. Okay, but let us discuss how this has come. Now let me take say 3-axis system. Okay, so this is 1, this is 2, this is 3. This is degree of freedom. Okay, so this is positive 1 axis, positive 2 axis, positive 3 axis. Now if we look at the values of, say let us take first mode 1, 0.8, 0.45. So first mode is 1, 0.8, 0.445. Second mode is 1 minus 0.55 minus 1.247. 1 minus 0.55 minus 1.247. Let's take third mode also. 1 minus 2.24 plus 1.8. 1 minus 2.24 plus 1.8. Yeah. Now let us plot the first mode. So first mode, this first coordinate value, so that is the top one, it is 1. So let us put 1. The second coordinate is 0.8. So in the second coordinate, let us go to 0.8. So this is 0.8. Okay, so let's call it as this as 1. This is third coordinate 0.445, all positive values. So this 0.445. So what we need to do is we need to draw a line so this is the first mode. This is first mode. So you can see on x coordinate or 1 coordinate we went up to 1. On second coordinate we went up to 0.8 and third coordinate we went up to 0.445. Then the second mode is, in the first coordinate it is 1 only, but in second coordinate is minus 0.55. So it is this value, and then third coordinate it is minus 1.2. So that means what? So 1 in that direction. So that means what? If we look at this coordinate system, so what will come is, so all positive is one side, So this A has two negatives and one positive. So two negatives means it will come on this plane below. So negative this one and then negative. So what happens is we will get something like this on the 1 -3 line and -2 line. So it is this quadrant below. So in that we are writing 1 minus 0.5 minus this one, and the third one is again 1, and this one second axis is negative. So negative means down, third axis is again positive. So that means what? Positive 1.8. So what we get is in this. So 1, then we go down, and then we come on this side. So it is this. So this is phi 1, this is phi 2, this is phi 3. So what I mean to say is this phi 1 will be perpendicular to this, and this is perpendicular to this. So that means what? Phi 1, phi 2, phi 3 are perpendicular. So in a way, if we transform and write this one, it will be something like this. This will be phi 1, this will be phi 2, this will be phi 3. So phi 1 is perpendicular to phi 2 line, and phi 1 is perpendicular to phi 3 line. Similarly, phi 2 is perpendicular to phi 3 line and is also perpendicular to phi 1 line. Phi 3 is perpendicular to phi 1 and phi 2, like this. So this is modal orthogonality. The same thing we have seen in the form of numerical problem. So in summary, what we have discussed in this class is how mode shapes are orthogonal. So this property of modal orthogonality we will use in converting a coupled equation into a decoupled equation. So if say usually mass matrix is always diagonal matrix, off diagonal terms are 0, so it is already uncoupled. But when it comes to damping matrix and stiffness matrix, these are coupled matrices. So that means off diagonal terms are all not 0. So what we can do is, if we pre-multiply and post-multiply with modal matrix, then all things will become diagonal terms. So we are converting say one coordinate system, so that is u1, u2, u3 into a system of q1, q2, q3. So that means n degrees of freedom system we are converting into n single degree of freedom system. So for that we use modal orthogonality principle of modal matrices.